All right, here we go. In this session, we are going to start looking at JSON Web Tokens, otherwise known as JWTs, otherwise known as JWTs, which I've always found a bit odd, but that is the intended or at least the accepted pronunciation. If you hear someone say JWT, we're talking about JSON Web Tokens. Now, this one is going to be a multi-parter. How many parts? I have no idea. The ecosystem behind these, the ways in which people use these are vast and complex, and honestly, it probably warrants multiple sessions. Well, I mean, it definitely warrants multiple sessions. I already put part 1 on there, but 2, 3, maybe. I think it might also be worth going into some of the frameworks and standards that rely on JWTs, talking about OAuth and some others in particular. It may also be worthwhile to look at some of the source code behind libraries that have had traditional vulnerabilities in handling JSON Web Tokens or JWTs. You'll note that I tend to rarely say JWTs. I just find it a bit strange myself. So I usually say JWTs. But yeah, there's much to consider. So why don't we get right into it? Definition. This is, as with other series of mine, my own, but largely derived from the RFC, where JSON Web Tokens are defined, and we'll talk about those in a moment. It is a URL-safe and cryptographically secured object representing claims to be transferred between two parties. It's part of the JOSE framework, which for the purposes of this video, we're just going to call it the Jose framework. I'm not sure about the pronunciation of that one, but we're calling it Jose for this video. Now, I did note that JWTs are URL safe. We're not going to get too much into all of the security issues and implications of JWTs, but you can put them in URLs. Should you is another question, and we'll talk about that eventually as well. So as I mentioned, it's kind of a complex and vast ecosystem, especially as far as technical standards and definitions. So JWTs fall under the JSON object signing and encryption ecosystem or framework, Jose, as I refer to it. And there are some RFCs that touch on these technologies that I excluded from here. This is just what I'm roughly calling the core set of RFCs that define a lot of the technology that we're going to be looking at. I'm just going to go through them quickly here, but most of these I touch on in the session. So we're covering it all. By the end of this lesson, you should be familiar with most of these RFCs, what they define, why they exist, and the relationship to JSON Web Tokens or JWTs. The first one being JSON Web Signatures, which deals with content that is secured with digital signatures or MACs. Then we have JSON Web Encryption, which are the encrypted variation of those. We have JSON Web Keys, which define a way of representing keys that are used for those cryptographic operations. We have JSON Web Algorithms that define the algorithms that are used and how they're named and referred to across that ecosystem. We finally, well, not finally, but then we have JSON Web Tokens or JWTs, which define a specific variation of these types of tokens. We have RFC 7520, which has some Jose examples, which we won't really look at. And finally, in this list, we have JWT best current practices. And there's a new draft here, which we're not going to get to in this session. That is going to be where we're going to go next session. We're going to go from all of the technical standards, definitions, how they work together. Then we're going to look at best practices. Then we're going to finally look at attacks, historical issues and vulnerabilities in libraries, what makes sense as far as testing tooling and so on. So I'm really thinking at this point that this is going to be a 3-parter series. So JSON Web Signature, JWS, we're going to start with these. This is defined by RFC 7515. So just sequentially, as far as numbering goes, it's the first in our list there. And this RFC defines the use of digital signatures or message authentication codes, so MACs, that secure JSON-based data, and they secure them in a specific way. So these are not encrypted tokens, but these are tokens for which their integrity and authenticity are guaranteed by the cryptography that is used to create the tokens. These are JSON. The tokens themselves are JSON data structures in totality, and they use a specific form of base64 encoding. They use a URL variant that we'll be talking about. And they consist of 3 parts. a header, which is known as the Jose header, a payload, and a signature. One thing to keep in mind is that so JWS, JSON tokens that are valid JWS tokens are not necessarily JWTs. And one really important aspect of JWS tokens to keep in mind is that they can support payloads, which is the middle component of those tokens, without those payloads having to be JSON. It can be effectively arbitrary data. And so you might see tokens like this in the wild that look like JWTs. You might be wanting to call them JWTs, but in fact they are not, depending on the type of data they're encoding, how they're working, how they're structured. And when speaking about the token structure, there are actually a few different ways that these tokens can be structured, but we're going to be focusing almost exclusively on what is known as the compact serialization, which is the standard URL safe way to structure the tokens. The reason why we're going to be focusing on this is because that is what JWTs are mandated to use. And this looks like serialized serialized JSON that is base64 encoded in 3 parts, and those are separated with little dots or periods. As you can see, I have circled in the image here. And so the first line up at the top with the base64 URL in it, that's indicating the algorithm to construct these. And then what the arrow is pointing to is what these tokens look like when they're produced. So a really quick way to identify a token that belongs to the, Jose framework broadly is one that is base64 encoded. A lot of the segments begin with EY, which we'll talk about in a moment why that is, and have these periods separating the different components of them. The signature computation produces a token that is protected by a signature. Technically, there is a variant where the signature can apply to the payload but not the header. We're just going to be looking at the protected header variant, which is where the signature is also applied to the header. And so the rough algorithm for that is down below. One thing that's important to keep in mind is the secret at the very end. That only applies when you're using an algorithm that requires a secret. So if you're using RSA for a signature, no secret is required. If you're using Mac with a hashing algorithm like SHA, for example, a secret is a crucial part of that that is used to create that token. And so therefore, you have different situations depending on the algorithm that you're using. And there are implications for that as far as security, but we won't talk about that in this session. Quick note about the base64 encoding that is used. It's a specific variation of base64 encoding known as base64 URL, and there is a specific RFC that defines it. It's 4648, and in particular, it's section 5 in that RFC. If you want to take a look at that, it's a quite short RFC. There's not much to this. One thing that is important to mention is that the trailing padding characters are omitted here. So when you're looking at tokens here, even though they're base64 encoded, you don't see those padding characters that build, you don't see them built into the token. That is fine because it can be inferred from the content as for the RFC. So if you're using a tool like CyberChef, there is a URL safe variant, and you'll see that it refers specifically to the RFC 4648, and it even indicates the section number. But one thing to note is that a lot of base64 parsers may still fail to parse the tokens if they're looking for or expecting the padding characters. So that's just one thing to keep in mind. Here is an example of a JWS token. Well, in this case, it is specifically a JWT, but it's still a JWS, and it's being decoded here. And you can see that that produces two segments of JSON, two JSON objects, and then at the end we have what looks like gibberish because that is the signature. It's not meant to be human read. It is the data corresponding to the cryptographic signature that signs that object. One thing to note also surrounding tooling, if you're using CyberChef, it does have a JWT decode feature, but this will strip seemingly and it doesn't, I don't think it has any options, but it strips the header and it strips the signature as well. So it just shows you the actual, the payload. So you might not be seeing all the information that you want to see as a security tester. Keep that in mind. As far as identifying base64 encoded JSON, this pattern will become very familiar to you as a security tester. When you base64 encode an opening curly brace and double quotes, your string is going to begin with the letters lowercase ey, and oftentimes you'll see ey and then a j, because a lot of characters will result in that specific pattern. So that's a pretty dead giveaway that you have some base64 encoded JSON. There, I mentioned, was another token structure, and this is the JSON serialization form, and that's what this looks like. We're not going to be discussing this. We're looking at it too much in detail. It's possible that you see it in different situations, so I thought it would be worth calling out on a slide, but we're basically going to skip right over that and move on now to talk about the Jose header, which of course we mentioned as being a key component of the JWS specification. Now we're going to talk about what it is. So this header describes the algorithm as well as a set, one or more or none optional properties called parameters. The parameter names themselves must be unique. The only mandatory one here for JWS and JWE is the alg parameter, which defines the algorithm that is used for JWS tokens. That's going to be the signature algorithm. And the structure of this, just like the payload, is of course serialized JSON, and it too gets base64 URL safe encoded. I noted before that a protected header is one that is covered by the signature, where the signature algorithm is applied to the header, and therefore you're guaranteeing in that token the integrity of the header, or at least you should be if your validation logic is working correctly. So below at the bottom of this slide are just some examples of what that header can look like. In the simplest case, you specify an algorithm, HS 256. In the case below, you specify an algorithm. You also indicate a type. It's a JWT. And then we have KID, which specifies an identifier for a specific key material. We're going to talk about some of these standard parameter values, and actually we're going to talk about them now. So in the JWS specification, there are registered parameters for the Jose header, and these are those. And I'm indicating here which RFC defines them. The alg one is also defined in 75.1.6, and all of these apply both to JWS and JWE tokens. JWEs we'll talk about momentarily. I'm not going to go into depth on a lot of these, just calling a few of them out. Alg, of course, is required. It indicates the algorithm that is in use. JKU is interesting from a security perspective. It can indicate a JWK key set that contains keys for use in relation to that token. You can also embed those with JWK. KID is a key identifier. You'll see some of these other ones from time to time. In a lot of implementations, usually you'll just see the algorithm and the type, TYP. And oftentimes that type will be JWT, but not always is that the case in security testing. There are other variations that you will encounter from time to time. Very important reference, if you're seeing a lot of JSON-based tokens, is this one, the IANA's JSON Web Signature and Encryption Header Parameters reference. It has a reference to those parameters and a lot of other helpful information. So if you see a token, you don't know what something is or does in its header, you can look it up here pretty quickly. This is a standard page to register those. Moving on to the next RFC, which would be 75.1.6, I believe. I probably should have put that reference in there. We have JSON Web Encryption. So this sets out a specification for not just ensuring the integrity and authenticity of tokens, but also adding in that confidentiality element by encrypting the actual payload content. So that JSON object or whatever your content is that you want to encrypt. and it's a little bit more complex. In this case, we have 5 parts in compact serialization. We have the header, then we have the content encryption key, or CEK. So this is the actual key that is used to do the encryption. That's built into the object, and that might sound a little bit confusing. It might sound like that is an insecure implementation because the key is right there. That key is encrypted, and we're going to talk about that in a moment. You also have the IV, or as I should have written, the initialization vector. We have, of course, our ciphertext, which is our main payload that we're caring about actually protecting and transmitting from system to system. And finally, we have an authentication tag as an integrity check for the ciphertext. Excuse me. Similar to JWS, the JWE standard supports multiple algorithms and different key types. It's seemingly less common than JWS variants. So as far as my personal experience in doing security testing, I remember very early on, my first time encountering JWE, thinking it was a standard JWT, and trying to decode it, and then being like, what the hell is this? It doesn't decode, I get gibberish. And then learning about the JWE specification and the encryption of these tokens. It's a little bit less common than non-encrypted variations that just have a signature, but you will still see it if you're testing a lot of systems. Compared to JWS, there are also a couple of additional registered parameters for the header. There is the enc, which specifies the encryption algorithm, and there's also zip, which optionally can compress content before encrypting. Here's a very simple example. We specify an algorithm, and then we specify an enc, which is the encryption algorithm. So these are different, and this can be a little bit confusing. The enc is the encryption algorithm that is used to encrypt the alg is the algorithm that is used to encrypt the encryption key, or the CEK, and then the enc algorithm, so AES here, you'll note, is a symmetric algorithm. It's AES 256 in GCM mode. It is an algorithm that is then used by the CEK in order to actually encrypt and decrypt the payload content, the plain text. And the reason why these are separate is that primarily efficiency. There are some other benefits, but by ensuring that the actual encryption algorithm is symmetric and avoiding encrypting and decrypting too much data with asymmetric algorithms, like the asymmetric component encrypts and decrypts the CEK, the actual encryption key, which then can apply symmetric encryption to the payload, which of course can be of varying size, and they can be quite big. So efficiency is the big argument here as to why that is split up, instead of just having your asymmetric algorithm do all of the encryption and decryption of your actual payload. Returning to the full header here, we also have the type, which specifies JWE, and there is a KID, which specifies a key name. That's not always going to be present. You'll find it in a lot of implementations, and in some implementations, it'll be there and not even used. Oftentimes, the key material that gets used by different systems is implicit, right? It's kind of built in. If a token arrives, it's going to be using a specific dedicated key that the developers have set up as far as that process goes, but not all the case. And in some cases, there might be systems that support the use of multiple keys. And we'll talk a little bit about that as we go. Yeah, that's everything on this slide. So if you take a token that is using JSON web encryption and you toss that into CyberChef and try to base64 decode it, you might get something like this, which looks obviously a lot less useful. And here, of course, we have the minimal combination of enc and alg, and then we have just ciphertext, which is meaningless to us because it is encrypted. And we cannot, with that token alone, decrypt it. Breaking it down, of course, compared to JWS, the JWS standard, there are more sections here. And so, here in this example, it looks like we've got a header and then we've got everything else. But if you look at the period delimiters in that string, there are actually multiple different components, as have already been discussed. First, you have the protected header Remember, that doesn't mean encrypted. That just means it's protected by the signature. And of course, that is base 64 encoded JSON. And so we can decode that and we can view that. We can view the basic properties of an encrypted JSON object just by decoding that header. But everything else is less meaningful to us. Of course, we have the encrypted key, which if we decode it, it's data that is encrypted. We have the initialization vector, which, again, data that we can't do much with without the key. We have the ciphertext, of course, which is our encrypted payload, and we have the authentication tag at the end. So these tend to be not that useful as far as viewing as a human, right? At least not without the appropriate key material. And just to emphasize the differences here between JWS and versus JWE, we have 3 parts in the JWS separated by 2 dots. And with the JSON web encryption base tokens, we have 5 parts separated by 4 dots. And of course, we have the distinction of confidentiality provided by JWTs. But I think that should all be very clear at this point. Now, finally, we're getting to JSON web tokens. So JSON web tokens are described as a profile or maybe like a type or a subset of JWS or JWE tokens. And that is because they have a more strictly defined structure compared to those. They're less flexible. They can be a type of JWS or a type of JWE, but not every JWS or JWE is going to qualify as a JWT. The payload in particular must be valid JSON and be using the compact serialization structure, which we've been focusing on. The payload in particular is called the claim set. So it is a set of key value pairs that are defined with JSON, similar to Jose header parameters. Registered claims that you can have within that within your payload are defined by the RFC, but you're not limited to registered claims. So claims are optional and also span across 3 different classifications. We have registered claims. These are the ones that are defined in the RFC and I guess also managed by the IANA. We have the public ones that are typically intended for shared use. So these would be systems that are using some collectively for some given purpose, and those should be in the IANA JSON Web Token Claims Registry. But finally, you can also just have any claim that you want. You can have arbitrary claims. So these are typically referred to as private. They're not registered. Often they're application specific. You develop an application for specific use. You have JWTs deployed for specific use. You've got custom claims within them. That's a relatively common pattern. Developers really are doing anything with these tokens out there, and oftentimes, of course, that leads to security issues, which is our goal as security testers to identify. But we can look at some of the common claims. So even though, developers are doing anything out there and they can do anything, you'll see a number of common claims that are shared, defined, and often built into standard libraries. So I would guess that in many cases when JWTs are deployed, the developers that are building those in may not even be aware of some of the claims that are built into those. They may be defaulted in depending on the library that is being used to implement them. So first we have the issuer that indicates the system that issued the token. We have the subject. We have the audience, the intended recipient of the token, the expiration time, the not valid before time, the time at which the token was issued at, and also a JWT identifier that can be used. But again, in practice, in the wild, you will see all kinds of different claims that exist in JWTs, and many of which might be application specific. Okay, here's another link to save. So this one is the JSON Web Token reference, and it contains a large number of claims that are in common use and publicly known. And when you're inspecting JWTs and trying to figure out how an application works and what it's doing with those values within those claims, this is probably a great starting point to take a look and see how those are defined, if they are defined. As far as common usage, JWTs are probably most often implemented as self-contained tokens. So I pulled in the definition from the OWASP ASVS v5 A self-contained token is a token that encapsulates one or more attributes that do not rely on server-side state or other external storage. These tokens ensure the authenticity and integrity of their contained attributes, enabling secure stateless information. So if we're thinking about client being browser and just a single server situation, server says, okay, I'm going to take some data that I know about you or am going to entrust to you, and I'm going to sign it, and I'm going to make it a JWT so that I know that I have created this token, and I'm going to give it to you. And so I'm going to just forget about it. But I can trust you when you send me a new token that information is valid because I can verify the signature, because you, the client, the browser, cannot sign the tokens. Only I, the server, can sign the tokens because I have the cryptographic material. I have the signing key. I sign the token, I know that it's valid, I give it to you, I forget about the information. I don't need to keep it. You are the steward now of that information because that information has its integrity kept in check by cryptography. So that's really the common pattern. And ultimately, though, the primary use, or probably the primary use case, is not just that single server and browser client situation, even though that's quite common, as we'll see, but the common, or again, intended use would be the secure transmission of claims between systems. You can have, this gives you a system where you can have an issuer and an audience, and those can be completely different systems managed by completely different organizations. And one of the benefits of having JSON Web Tokens is that they provide a standard defined structure. So we share an understanding of how the tokens are structured. And because they allow us to use asymmetric cryptography in a certain way, one system can sign a token, send it somewhere else, and that other system can have the corresponding certificate to validate that that token has been appropriately signed. And so one system can trust the data that is coming from another, even if it's not encrypted and it's going through untrusted parties in the middle. And that's often where you'll also see this pattern of JWT token usage. You'll see tokens go through untrusted parties, right? And if you're a web browser, or if you're a user of a web browser, you're receiving tokens that give you oftentimes privileges within an application. And it's not that it trusts you to be a steward to determine what privileges you should have, but that the properties of the token ensure its integrity, so it can send it to other systems without concern for that integrity being broken. Well, unless there are security issues, vulnerabilities, and so on, which we will eventually get to. One of the very common patterns of JWTs is using them in place of what you'll traditionally hear referred to as a stateful session management mechanism, and we're going to talk about this in the next slide. But it's also commonly used in different authentication authorization flows using OpenID Connect and OAuth 2.0. We won't go into too much detail on those in this session. But here's probably one of the most common uses. You will see, at least I commonly see this pattern. You have a client, browser, application, and it submits an authentication request to some authentication server that maybe also is an API, so also a server that has the resources you're trying to access. And when you authenticate, it gives you a JWT and it says, okay, here's what you have access to based on the claims that are baked into that JWT, and you store that JWT in some capacity. And then when you send subsequent requests to that same server, you say, hey, I'd like to do this now. Here's my JWT. It says I should have access to these things. And that same server will verify the token. Of course, the token, it's not keeping track of it. It has created it, it has sent it to you, and it has forgotten it. And that is why these systems are often referred to as stateless, because the server is not tracking the state of that token. Like, it's not like a traditional session identifier that is generated and managed on the server side. And that comes with a few downsides, as we'll see in a moment. But ultimately, it verifies that token, which it can do cryptographically, and then it will, if you're authorized, send back data or whatever. And of course, because it's stateless, it needs to do a little bit of cryptography, but it doesn't need a database lookup. And this may be one of the reasons why these took off in popularity for developers looking for ways to offload the use or negate the use or the need for databases or different types of caches for session storage and that sort of thing. But as you can find out pretty quickly, The security community broadly recommends against the use of JWTs as a so-called stateless mechanism to manage sessions. And I will say that a lot of the information that's presented in a lot of these is a little bit out of date, and the consensus and the thinking about risk of using tokens in this way has shifted a lot. In particular, I'll give you one example. One example that's often cited is, well, if you're using JSON Web Tokens as part of a stateless mechanism, you're storing those in the browser's local storage, and that's bad because JavaScript can access those tokens, right? So if there's a cross-site scripting vulnerability, it can access those tokens, and then an attacker can do whatever with your token. And that is the motivation behind HTTP-only cookies. That is why those exist. But there are a few counter arguments to this, and the main one being that in practice, it doesn't seem like protecting different session objects and identifiers from JavaScript has really helped mitigate the risk and impact of cross-site scripting. When you have cross-site scripting on an application, even if you can't retrieve the appropriate session object or whatever gets you access to that user session, you can still conduct the same actions on that user's behalf. So it increases maybe the complexity and the effort a little bit as far as the attack, but I'm not familiar with any cases where, like an HTTP-only cookie was the one thing that stopped an attacker with cross-site scripting from exploiting something. It just doesn't seem to be that effective of a control, even though you think about it and you're like, well, if we have that protection, why not implement it? And true enough, we actually can with JSON Web Tokens, because you can also just use browser cookies as a mechanism to transmit them. That being said, it appears to be a very uncommon practice. And there is a kind of pro argument for using JSON Web Tokens, or really any tokens outside of browser cookies, and that's that you often mitigate cross-site request forgery attacks. Of course, the exception being client-side attacks where you can abuse client-side functionality, like client-side path traversal attacks, where you can cause the client-side JavaScript logic to automatically send the token regardless. We're not going to go into details for that. But all that being said, there are pros and cons to using it. In my mind, the biggest challenge and limitation and ultimately risk from using JSON Web Tokens is the fact that, or rather from using them in a stateless manner, is that once a server creates that and decides it's going to trust it, it has no way of revoking it because it's not keeping track of it. So if you have a situation where an attacker obtains one of those tokens, you can't have a system that revokes that. Users can't go in, log into their application, look at their active sessions and say, I'd like to revoke this one. Assuming that token has an expiration time, that token is valid until it expires. There's no way for a server to track specific ones and revoke them. Now, there are ways around this. You can implement applications that do have some type of stateful tracking mechanism using a database to keep track of elements of JWTs that are built into the payload, but that becomes quite complex. And so I think the greatest argument against using JWTs for session management is just that they're overly complex. They're a far too complex problem for a solution that has many, many easier approaches. And probably the strongest attribute of applications that correlates with their insecurity and the increase in vulnerabilities is complexity. The more complex an application is, the harder it is to secure. And we've seen that over and over again. So my biggest argument against is they're very complex. We've already seen a large number of RFCs that correspond to them. There are many more we have not even touched on. We haven't even looked at best practices yet or the common flaws. JWTs add massive complexity to applications in many cases, and that's the biggest argument against using them this way. So probably one of the most popular talks that touches on this is from Philippe Derick, and the talk is titled "The Parts of JWT Security Nobody Talks About." This is quite old now. This is an old talk. I don't know how he feels presently, but he was a very strong advocate against this particular pattern. Of course, this slide is directly from his talk. YouTube link is down at the bottom. I encourage you, if you're very passionate about JWTs, to go and give it a watch. He's been an advocate on the security of JWTs for quite some time. And just to be a little complete, this is another pattern that you're also likely to see. And that is a situation where, again, we have we'll say browser client or an application that reaches out first to a dedicated authorization server, which is our issuer, but the audience is actually a different system. That is our resource server. So this is the type of flow roughly that you see in OAuth 2.0 / OpenID Connect. And the authorization server provides you the token, but then when you send your API request, you're sending it to the resource server. Well, service or server. And there you're sending it your token, which potentially it is able to validate. Depends on the architecture there. And so this is a situation where the resource server is trusting the issuer to create valid tokens where their integrity is maintained. Also a common pattern. Is it more common than the original pattern I showed? I'm not really sure. I haven't done a comprehensive survey. One thing we haven't talked about but has been referenced a couple times is the JSON web key, which is yet another RFC, RFC 7517, I believe it is. And this is a standard that describes a way to transmit keys on the web using what? JSON. Everything is JSON now, right? So these are, there's a typo there. These consist of both required and potentially optional JW key members within a JSON object. And the simple example shown here is an RSA public key. And of course, it has the key type, it has the intended use, it has an identifier, it has an algorithm, and then it has some interesting members that you're probably not familiar with if you haven't seen these before. And don't worry, we're going to demystify these right now. This is a not fully comprehensive table, but I think it's pretty close. The only required component or member of a JSON web key is the key type, which specifies the key type. And then all the other ones, I mean, are, I guess, technically optional, but if you only have a key type and then nothing else, you don't really have much of a JSON web key, right? There looks to be a bit of a typo there. The second one should be use. Apologies for that. As you can see, the example is correct, but I mistyped big time in that second row. That should be use, and that can indicate whether it's for signatures or encryption. We have key operations or key ops, which is the permitted operations for that key. We have the algorithm in use, of course, very important. The key identifier, which you've probably seen previously, can appear within the header, the Jose header, a key identifier which attaches a JSON web token, as an example, to specific key material that can be defined within a JSON web key. And then we have the other member components that are dependent on the type of keys. So if you're looking at an RSA key, which we were above, we have N and E, for example, which are the public members. But you can also have private members that let you essentially fully recreate the capabilities as if you had that full private RSA key. So there's a distinction here between the public and private members that is important to consider. We also can extend JSON web keys to what you'll probably more commonly see online, which would be JSON web key sets. And these are JSON objects where we effectively have an array of keys. So multiple keys can be bundled into a JW key set, making it a JWKS. And these are ones I said you're more likely to encounter because they're commonly used to expose keys. And these are some of the forms that you might see them. The most common being the one associated with OpenID Connect or OAuth 2.0 providers, though not exclusively. You'll see this pattern as part of other systems as well. And that is under the well-known path segment, a file jwks.json, because of course we're dealing with JSON objects that contain keys. And I've noted at the bottom, this might be the one exception to this session, which mostly is focusing on the underlying technology and not the security issues. But I did note one possible security issue. I don't think I've seen this myself, but in theory it's possible, and I believe I've heard of it happening. I mentioned some of the members of different algorithms sets can be private. And so, of course, if you accidentally publish those when you don't intend to, you could be exposing the capabilities or essentially exposing your entire key. And these files are likely where you would see that happening. Moving on to yet another RFC. We now have RFC 7518 JSON Web Algorithms. This one's perhaps a little bit less interesting. It specifies registered algorithms with specific identifiers. So it basically gives us a name when we're making tokens, gives us names so we can refer uniquely to specific algorithms to try and avoid, I guess, algorithm confusion type issues, or any scenario where you have disagreement over the algorithm to use based on a name. This is a standardization of names, and it can be used with JWS, JWK, JWT, JWE. Once again, I linked this same link before, the Jose header resource from IANA. It also has, I believe, a full summary of the present algorithms that are supported. I have a small summary down at the bottom indicating some signature MAC algorithms, some key management algorithms, and some content encryption algorithms. And that brings us to the last referenced RFC, which is the JSON Web Token Best Current Practices. And for that, we're going to be looking at the latest current draft, and that's going to be covered in next session. There was so much to cover this one. I thought it would take too much time to go into all of the best practices. So that does it for today. I hope everyone looks forward to part 2.